Hey, hi everyone. I welcome you all to this DSA Bootcamp. First of all, I introduce our star mentor, Apaar Kamal sir, who is an upcoming SD at Google, SD intern at Zomato, Samsung, DTU Master 6 star. Welcoming you, sir.
Hello,
Today
Rita.
he is Hi, sir. Today he is here for presenting the topics trees. Yes, sir.
Right. So, shall I start?
Yes, sir. Sure.
Okay. So, I'll share the screen.
Okay, sir.
Just let me know that am I visible or not. Is the
Yes,
screen
sir. You're
visible?
visible. Yes, sir.
Okay, cool. So, hello everyone. I have been warmly introduced by Harita, of course. And so today we'll be starting the basics of trees, and we'll slightly go towards the intermediate level, you know. And let me introduce a little more about myself. So I've been a mentor at Coding Blocks from past 2 years, and I will just join Google as an SDE from in upcoming July. And I got offers from Coordination Zomato, right? And recently I finished my 6 month intern at Zomato, and that was a very big experience. Right. So, guys, most of you might be wondering that what all is required to get into like big giants companies, right? So, I'd just say one thing, that just go for any good topic, go for some good topics, and practice like around 50 to 100 problems on those good topics, and that would be more than enough, right? So, if so it's just a little bit introduction. I'm like warming up, so I'll just continue after this session, right? So yeah, so what I wanted to tell was that if you are a beginner, if you are an intermediate, and you really want to crack some interviews of very very big companies, so it's very simple and it's very easy, right? It just requires some persistent work, and nothing much, right? So the thing is that just get a course. If you are not a self learner, if you think that you require someone to teach you, or you require some guidance and all, just get a course, get in touch with your mentor, and whatever topic you read, right, like solve problems from it. You can always try lead code problems, because lead code problems are like those problems which are being directly asked in the interviews, right? So what's better, right? It's like practicing from RD Sharma in mathematics, right? So those are the problems that we can see directly in the interviews that we face, right? Lots of problems from lead code. And that's a humble suggestion basically, and it's up to you. And yeah, so this is the major point, guys. So study everything, right? You can even deep dive into competitive programming if you wish to, but it's not a compulsory, or it's not needed to crack some good interviews, right? Competitive programming is not must, right? You can do it if you like it, otherwise it's not really needed. So it's basically like you are training yourself, you are trying to get in shape, like by going for a jog and doing some exercises. That is data structures and algorithms, right? But if you are like into competitive programming, that is like you are actually going to a gym to like compete with people, train yourself better, to achieve greater heights in less time, right? So that's the difference between doing normal data structures and algorithms for interviews, and going for competitive programming in uh, for these interviews, right? So CP is a whole different thing. Of course, I did like I'm now. I think it's been like 3 years I have been doing CP, and I still do it, right? I still give some contests. I still enjoy it, right? But it's not for cracking some interviews and all. It's not for that purpose, because I've already reached where I wanted to, and I will join Google in July. I don't want to so that's the level, but still I'm doing CP, right? Why? Because I enjoy it. So do CP only when you enjoy it. It's not for some DSA purposes and all, right? So I hope that's enough. That's a good warm up, and let's begin with today's topic. And I've been told that we have like beginner students here, like beginner to intermediate students. So firstly, in the first half, like around 45 minutes, I'll take some basic things that are required, like DFS, BFS, what are trees, its traversals, how to represent trees, right? How to code them. I'll take all of that. And in the next half, in the second half, I'll try to cover some intermediate topics. Cool, like printing paths in trees. There are a lot of good problems available, right? I'll pick few of them. Cool. So let's begin with the topic. So I hope the screen is completely visible. And
Is so visible.
okay, so this is Sublime. Cool. So guys, let's begin with trees, right? So what is a tree structure, and what are its differences from graph? Like how is it differentiated from graphs? And just a second, let me remove this. Hmm. So what is a tree? How does it differentiate between graphs, and what is the actual difference between graphs and trees, right? So we will see everything of it, right? And we will see various different like definitions of trees, and we will see which suits it the most. Cool. So guys, what is a graph? Let's begin with graph. So graph is a structure which contains some nodes and edges, and those edges are actually connecting those nodes, right? So let me give you some examples of graphs. So let's say this is a graph, right? This can be another graph, right? And there can be many more graphs. So these two, right? If I just number them something else, so let's number this as 6, 7, and 8, right? So these two also make a graph. We have nodes from 1 2 3 4 5 6 7 8, but we have two different components here, right? So this is another graph. So as we can see, what is a graph? Graph is a simple structure with nodes and edges, right? And those edges are between two nodes. Any edges between two nodes that joins those two nodes, right? Now we know that edges can be directional or bidirectional, or let's say undirectional, right? So what does this mean, that edges are directional or undirectional? We can have directed edges, we can have undirected edges. So let me like frame a little structure. So this is a graph, right? But here we have arrows, right? We have arrows instead of like lines. So what are these arrows? These are directed edges. That means from 1 you can go to 2, right? From 1 we can go to 2, but from 2 we cannot go to 1 directly, right? So this is a single directional unidirectional edge, that we have only paths from 1 to 2 but not from 2 to 1. Similarly, we have paths from 1 to 3 but not to 3 to 1, right? And 2 to 3 and not 3 to 2, right? Now let me make us again us the same graph. So it's 1 2 3, same. Cool. Yeah. So this is 1, 2, and 3. Now, guys, we can see that we don't have edges in the. We don't have directions in our edges. So if we don't have directions in our edges, that means we can travel anyway, right? That means if I have an edge from U to V, that I can travel from U to V also, and V to U also, right? So they are from both the directions. Cool. So these are some graphs, right? So this is a directed graph, this is undirected graph, right? So graph which contains directed edges are called directed graphs, and the graphs which contain uh, undirected edges are undirected graphs. Cool. So I hope this part is very clear, that what are graphs. This is a normal representation, right? So guys, in graphs, if I have we'll always say we have n nodes and m edges, right? So always remember, what does n and m mean? If I ever say n, that means the number of nodes, the total number of nodes. And what are edges? The total number of edges, right? So firstly, what are n nodes and m edges? So let's say I have n equals to 5 for my graph. So I'll have some 5 nodes in my graph. So it's not necessary, guys, that every of these nodes will contain an edge, and it's also not necessary that every node is associated with an edge. It's not compulsory, right? So for example, I can have m equals to 0 edges. So guys, this is a graph, right? This is a graph in which no node is connected to no other node, right? Any pair of node is not connected in this. Cool. Now I can have a graph which with m equals to 1 edge. What does this mean? Let's say I have only one edge that is between 1 and 3. So this is another graph, right? But this is not a tree. Cool. Now I hope you have completely understood what are graphs. Now let's differentiate between graphs and trees, right? So when I was in like secondary school, I used to learn things by actually finding their differences, right? That this is different from this. So by using that, I used to learn things, right? So let's find differences between trees and graphs, right? So cool. So can are there any comments? Is there anything regarding comments, Harita? Ki I'm solving doubts or something like that.
One moment, sir.
No, I mean, is there something like interacting something in this, or is it I'm piecing in them?
No, sir, you can continue.
Okay. So yeah, so from trees, let's begin with trees and graphs, right? So this is the main topic of our lecture, and of course, I'm like starting from very basic, right? I first explained graphs. Now we'll move on to trees and another easy topic. So we will see various definitions of trees, right? And then its properties. So what is a tree, guys? It is a graph with spatial conditions, right? So tree is a graph with, or let's say it is a connected graph, connected graph with no cycles. There are various definitions of it. I can frame it any way, but I'll explain you all of them one by one, right? So tree is a connected graph with no cycles. Let's understand what is a connected graph first. So we know what is a graph. Now we should understand what is a connected graph, and then we'll see what are cycles. Cool. So yeah. So as I took above examples, guys. So tell me, let's talk about this graph, right? So of course you can't tell me because it's not interactive. So let's talk about this graph, guys. Is it connected or is it not connected or what? Of course it is connected, right? So what is a connected graph? What is a connected graph? A connected graph is a graph in which every pair of nodes can be, there's a path between every pair of nodes, right? So let me write it, connected graph. So that means that there's a path between every pair of nodes, right? Path between every pair of nodes. Pardon my handwriting, guys. So so connected graph has a path between every pair of nodes, right? So let us see whether it is connected or not. So we generally say connected in terms of undirected graphs, right? In directed graph, we have a special word called strongly. So if you will deep dive into graphs and trees, or if you already know, so what do we say? We don't say, okay, cool. So we don't say that it is a strongly connected. We say for directed graphs that it is a strongly connected component, right? We never say that it is a connected component in case of directed graphs. So there are whole set of algorithms to find strongly connected components, right, in directed graphs. So in this workshop, guys, I will be focusing mainly on undirected graphs, right? So undirected graphs and undirected trees. So we won't be going into directed graphs and directed trees. Cool, because directed graphs and trees have their own set of algorithms to solve it, right? So we will like focus more generally on undirected graphs so that we can understand directed graphs later from it, right? So what is a connected graph? If every pair of vertices has a path between them, right? So here we can see that we can easily go from 1 to 2 by an edge. We can easily go from 1 to 3 by an edge. We can easily go to 2 and 3 by an edge, right? Let's talk about this, guys. Let's talk about this example. Let's take whole of this as a graph. this is a complete, this whole of it is a graph, right? This graph has nodes from 1 to 8. Cool. So guys, think and think and tell that is it a connected graph? No, right? Why? Because from 1 I cannot go to 8. From 1 I cannot go to 7, right? Because there is no path which will take me from 1 to 6, 1 to 7, or 1 to 8, right? So from this component I cannot go to this component, and vice versa. So it's not a connected graph, right? It is a disconnected graph. It has various components, right? It has various connected components in it, but it is generally disconnected. So coming back to the definition, guys, so what will be a connected graph? A graph in which every pair of vertices has a path between them, right? So no matter how big it is, let me make it. So this is a connected graph. How? Because from every pair of from any node I can go to any other node. If I start from 1, I want to go to 6, then I can go this way: 1 to 2, go to 7, go to 8, go to 6, right? So every pair of node is connected, right? So we don't have some disconnected components, right? Now okay, so this was about connected graph, right? So both of these terms should be clear. Now let us understand what are cycles. And then we will see some spatial properties of trees. Then we will see how to represent trees, how to code trees. Then we will start with their traversals. And after that, we'll come to some medium level algorithms for trees. Cool. So what is a tree is a connected graph with no cycles. Cool. Now let's say if this is a graph, right? But this is not a tree. Why? Because this contains cycles. Cool. So what is a cycle, guys? Cycle means that if I start from you, I go to some paths and I come back to you. So that's a cycle in my graph, right? That means I'm starting from some vertex, going to some other vertex, covering some set of edges and coming back to the source vertex again, right? That means I'm ending from where I started by covering some vertices. So in this case, what happens is we don't use any edge twice. All the edges in my cycle should be unique. So basically what it means is that if I started from 1 and I go to 2, that means this edge from 1 to 2 is traversed, right? Now I cannot traverse it again. I cannot say go from 1 to 2 and then again back to 1. No. Why? Because I have already traversed this edge. So there is no cycle in this graph 1 to 2, right? Let's talk about another graph. Let's say 1 to 2, 3. Is there a cycle in this graph? Yes. Why? Because if I go this way, 1, 2, 3, and then back to 1, this is a cycle, right? In this above graph, we can see that there are many cycles in this, many cycles. This can be one of the cycles, 1, 2, 3, 4. Another cycle can be this, right? One cycle can be 1, 4, 3, 5, 6, 8, 7, 2, 1, and the next cycle can be 5, 6, 8, 5, right? 5, 6, 8, 5. Another cycle can be 3, 5, 6, 8, 7, 2, 3. Cool, guys. So here we can see that we have various cycles in my graph. And always remember, guys, that trees and graphs are the favorite topic of any interviewer. Why? Because in trees and graphs alone, there are so many algorithms and so many problems. I was asked a problem in a very, very big company, and that problem was like it wasn't directly looking that it can be solved using trees and graphs, but that problem was actually converting to a graph problem which was using some algorithm on trees, right? So these trees and graphs, they have a huge set of algorithms, right? And of course those algorithms have some better complexities too, right? So what I would say is that these do not ever skip trees and graphs before you give an interview, right? Completely understand and solve trees and graphs and dynamic programming. These two topics are most asked in any interview. Like 80% of the problems consist of these two topics only. Cool. So coming back to the topic, guys. So here we can see that this is not a tree, it's a graph. Why? Because we have cycles. Now what we want to make is, we want to say that I want connected graph with no cycles, right? So let me make some connected graphs with no cycles. So if I talk about this right graph, that is only about this graph, 1 2 3 4 5, right? So if I talk about this graph, guys, then we can easily see that it is a tree. How can we easily see that? Because it is connected and it has no cycles, right? If I go from 1 to 3, I cannot come back to 1, right? I cannot come back to a same vertex again. There's no cycle in this graph, so it's a tree, right? Because it is connected and there are no cycles. Let's take some other examples, and then we move on to some properties. So guys, this is again a tree, right? And what if I do this 1 2 3 4? Now it's not a tree. Why? Because I have got a cycle in this. Cool. Let's talk about this graph. So guys, think and tell. Of course, you can't tell. Think that whether it is a tree or not. So this is not a tree, right? Why? Because it is disconnected, right? So mostly, if in problem, so in the problem statement, if it is written that you have been given a structure which is connected and has no cycles, then directly understand that it is a tree. Cool. So this was like one of the definitions of trees, and I hope you have completely understood this definition, that what are cycles, what are graph, what is a connected graph with no cycles, right? So now what you can do is, you can even try making some graphs which are connect. Okay, just a second, guys. I need to switch place, and I'll be back in 2 minutes.
Hey everyone. Uh, so I think Kamal sir will be joining soon. If you have any queries regarding bootcamp, you guys can ask in the comment section. We are having our contest uh, tomorrow, and soon the timings and all the stuff will be shared. If you guys have any queries regarding the contest, you can ask right now. And yeah, sir has just joined. And
Yeah, sorry for the interruption.
no
There's
worries.
there's some construction work going on, so I need to switch place so that uh, I don't get enough noise, right?
No worries, sir.
Okay, so let me continue. So I hope it is going fine. If anyone has any doubts, you can let me know, right? Okay, so as I can see the comments here, DP on tree is the demand, but I've been told that for beginners. Okay, got it. Not as such interesting queries here. So I'll continue with my workshop. Right, right. So, so where were we? This is a disconnected graph, right?
Uh,
So,
so,
if you
So
if
your
you
voice
want to
is
connect, sir, if you want to connect with the audience, you can join the same link of the YouTube, and you can read your comments out, these comments out. I can share the link in private chat as well.
I can also already see some comments over here on the right hand side of my screen.
Yeah, yeah, yeah. Comments will be there. Okay.
Yeah, so it's already there, right? Private chat and comments. It's a tab.
Oh,
Cool, no
okay.
problem. So is the screen visible?
Yeah, your screen is visible.
Okay, so great. So guys, let's come back to the topic. So I hope you understood what is trees and what are trees and how they can be defined, how they can be like understood by reading a problem statement, right? Now let's move on to some properties of trees. So here's this one interesting property, guys, that if a tree has n nodes, then m will always be equal to n minus 1. That is, the number of edges in my tree, number of edges in the tree will always be equal to node numbers minus 1, right? So what does this mean, guys? Matlab, why is this property even coming up here? So as we know that we have n nodes. So firstly, let's say we have 0 edge in a tree, and let's make some edges, and then we'll connect these nodes by making some edges. So let's say we have some 5 nodes, n equals to 5. Cool. So how many edges are required to make this graph is connected? So of course we can see that as we know, let's say we have a chain, right? Let's say we have a chain, 1, 2, 3, 4, 5. So let's say we have a chain. That means these 1 and 2 will be connected, 2 and 3 will be connected, 3 and 4 will be connected, and 4 and 5 will be connected, right? So what are the minimum number of edges which are required to connect all the nodes to each other to make it a connected component? 4, right? So if I have 5 nodes, 4 edges are required. So guys, think that if I add one more edge anywhere, right? Let's say if I add an edge from 1 to 3, like anywhere between any two nodes, if you add an edge, then that will result in a cycle, right? That means after n minus 1 edges, if any, if at least one more edge I add into this graph, then I'll get a cycle. Why is that so? See, it's a very simple logic, guys, that if I add any edge from 1 to, let's say, any node, right? So we know that 1 to 4 were already connected by 3. So there was this path from 1 to 4, like which was already a connected path. Now I've got a second path, that means a returning path from 1, which is by adding an edge from 4 to 1, right? So this whole is a cycle now, right? So what I mean to say is that if I have a connected graph, let's say I have some connected graph here which has no cycles, right? And if I add any edge inside any of the two nodes here, right, any edge, that will always result in a cycle. Why? Because if I'm adding an edge between a pair u and v, that there is already a path between u and v, already a path between u and v, right? That why is there already a path between u and v? Because it is connected already, right? It is connected, so there is a path from u to v. And if I add an edge from u to v directly, right, that's what it means now. If I add an edge in a connected graph, so if I add an edge, now there is a second path from u to v. So from first path I can go from u to v, first path, that was an already connected path, and then there is this edge which I am adding from between u and v, so this will give me a second path. So if I get these two paths, then this will make me a cycle. Cool. So if I add more than n minus 1 edges inside any of the graph, right, see, my first priority is to make this graph connected, right? So how can I make a graph connected? By adding at least n minus 1 edges, I can make a graph connected, right? See, some of you guys might be thinking that if m is equal to 4, that is, if I have 4 edges, then I can like make it a tree, right? I can make all of them connected to each other, right? But there is this way also, that 1 to 5, 5 to 2, 1 to 2, and 1 to 3, right? So as we can easily see that we have a cycle here, and also it is not a connected graph, as 4 is an isolated node, right? So the important thing to note here is that we have to add edges. We have as many edges as we need, but we only need n minus 1 edges. to make the graph as a connected graph. Cool. So this was about the edges property that um yeah so this was about the edges property that total number of edges will be equal to node minus 1, right? Then it will be a tree. So if it is a connected graph, right, so let's write some second definition here. So if it is connected graph with n minus 1 edges, then it is a tree. Cool, guys. So I hope you are getting this point. If it is a connected graph with n minus 1 edges, then it is a tree, right? Both of these are like compulsory. Writing connected graph is compulsory and writing n minus 1 edges is compulsory, right? So this is a second definition of trees. The first was connected graph with no cycles. The second is connected graph with n minus 1 edges, right? See, if I have n edges, let's say if I have n edges, then obviously there will be a cycle in my graph. Obviously. Why? Because I need only n minus 1 edges to connect. I have one extra edge. So wherever I put that extra edge, I'll get a cycle, right? So this is the second definition of trees. Now let's move on to some third definition of trees. Let's understand few more properties of trees so that we can redefine trees. Cool. So third definition is that we, instead of saying connected graph with no cycles or connected graph with n minus 1 edges, we can directly say that every pair of nodes or vertices have exactly one path between them, right? So try and understand it like carefully. What did I say? That if I have a graph in which every pair of node has exactly one path between them, right, then it's a tree. So you can easily see that this property that every pair of node has exactly one path, that means it is a connected graph, of course, because that's what it means, na. Every pair of node has exactly one path, right? So if every pair of node has exactly one path, that means they are connected, then only they can have one path between them, right? And secondly, it is key. So yeah, the connected property is done. It is connected is done, right? Because we can easily see that there is exactly one path between them. That means there is a path. Cool. And the next property is the cycle one, that it should not have a cycle, right? Then only it will be a tree. So from this definition, we can easily see that there is no cycle in my graph. If a graph has this definition, why? Because every pair of node has exactly one path, right? It is not at least one path. It is exactly one path. So if every pair of node has exactly one path between them, then it will be a tree, right? Because there are no cycles in that tree. Cool, guys. I hope this part is very clear why exactly one is written. That means it has no cycles. And of course, this is another definition of trees, that it can have n minus 1 edges, right? So that was like about definitions of trees. So in various problem statement, it will be said that every pair of, that you have a graph in which every pair of node has exactly one path between them. So there is no mention of whether it is connected or not. There is no mention of whether it has cycle or not. There is no mention of how many edges it will have or not, right? So this alone definition defines itself only, right? That is, it is connected because there's a path, there's no cycle because there's one path, exactly one path. Cool. So yeah, I hope beginners like, it's really being interesting for beginners because I'm teaching according to some beginner level. Means I'm the only mentor at Coding Blocks who has taken all types of batches, like all Launchpad, Algo plus plus, and then competitive programming batches. I've taught every type of student, like from basic to intermediate to advanced level, right? So yeah, so I've been told that we have to like keep in mind that we have beginners here, right? So this was about beginners, right? So here the beginner part is done, definitions and definitions of trees. And now let us move on to a little move on to one level above. And what we will do in this one is we will understand that how we can represent trees uh, in code, right? Because guys, in the end, after understanding all the concept, all the algorithms, we have to code, right? There won't be any technical interview in which you won't be asked to code. You have to code, right? So no matter whatever the interviewer is, or like whatever he's trying to ask, you have to code it in the end. So let us figure out how to represent these tree structures in my code, and we will also code it out. Cool. So I've already like Sublime Text open here, and we'll code in C++. Cool. So let me erase this. Right. So first of all, let's understand. So let's make a simple tree. Now guys, let me deviate a little and let me tell you some types of trees. Right. So we have already understood what are different types of trees on the basis of their edge directions. So right, so we can have some directed trees also, we can have undirected trees also. It completely depends on the problem statement, right? So here we are considering about directed trees, sorry, undirected trees. Now what we need to understand is that if I have these trees, then what are their different types, right? So we can have weighted tree, or we can have unweighted trees, right? So guys, what are weighted trees and unweighted trees? It's very simple. If any edge in my tree has a weight, right? So if my edges in the tree have weights on them, then they are weighted trees. Otherwise they are unweighted trees, and every edges has a constant weight on them. So let me give you an example. So making a very simple tree structure here, right? So this is a tree, we can see also it is a chain, but let's consider it a tree right now. And here we can see that all these edges do not have any weights on them. So what we generally say, if the tree is unweighted, then all the edges have one weight on them, right? So we take one constant value, that is one, that 2 and 5 are one distance apart, 1 and 5 are two distances apart, right? That is 1 to 5. And 5 and 4 are four distances apart. Cool guys. So this is about weighted and unweighted tree. So this is an unweighted tree. Unweighted tree. Now let us understand about weighted trees. So again, making the same structure, guys. Now what I say is that the distance between 2 and 5 is 4. 1 and 2 is 3. 1 and 3 is 2. And 3 and 4 is 10. Now guys, these edges between any pair of nodes, they have weights on them, right? So if edges have weights on them, then it's a weighted tree. Cool. So now if I say that how far is 3 from 5, what's the distance between 3 and 5? Then simply distance between 3 and 5 is 2 plus 3 plus 4, 9. Cool guys. So I hope this part is clear, that trees can be classified on the weight on the basis of the weights on the edges, right? Now let's have another classifications of trees. So the second classification on trees is on the basis of number of child they have. So on the basis of number of child they have, right? So what we say is that we have a binary tree. What is a binary tree? So in binary tree, a node can have let's say at most two childs, right? So guys, this can be a binary tree. Let me give you an example, right? So guys, to understand what is a node, what are the child, what is a child, right? Let us understand some few terms that are called root, root of a tree, what are parents in a tree, what are child nodes in a tree, what are ancestors in a tree. Cool. So let's understand these terms one by one, and let's like take example of this tree itself. Cool. So what is a root node, guys? So we know that if this is a structure, I can pick up any node and like hang the whole tree from that node. That is, right now the root node is 1, right? But similar structure can also be hanged by using 5 as the root node. Let me give you an example. If 5 is here, then 3 is connected to 5. Then 3 has one child 4, one child 1. Then 1 has 2 and 2 is 6. So we can easily see, guys, that both of these structures are same. All the nodes are same, all the edges are same. But what's the difference, guys? Difference is of the root node. Earlier we have 1 as the root node, now we have 5 as the root node. Similarly, guys, we can have 2 as the root node. 2, right? So from 2 I can have 6, I can have 1. From 1 I have 3, 3 I have 4, and 3 I have 5. So this is another same structure of the above tree, right? So what's the difference? The only difference is the root node, right? So guys, root node is the most important node of my tree, right? Because root node actually tells me that what can be parents, what can be childs, and what are ancestors, right? So these properties of parent, child, and ancestor depends on the root node, right? So right now if I say that 1 is the root node, then let me write it. 1 is the root node, right? So according to 1, 2 and 3 are its child, right? Because from 1, 2 is connected, from 1, 3 is connected. So 2 and 3 are child of 1. And what is 1? It is parent of 2 and 3, right? So child and parent, we can understand that. If 2 is a child of 1, 1 is a parent of 2. Cool. So 1 is a root node. So what are parents of 2? What is a parent of 2? 1 is a parent of 2, 3 is a 1 is another parent of 3. Now, what is the parent of 6? 2 is the parent of 6, right? And what is parent of 4? 3 is the parent of 4. And what is the parent of 5? Again, 3 is the parent of 5. So I hope this part is being clear, that what are parents, what are child, what are ancestors over here, right? Oh, okay. So we haven't gone through ancestors. So let us understand what are ancestors. Yeah. So first, before that, let us see. Let's try to understand this part, guys. That in this given example, one was parent of 3, but in this example, guys, here 5 is the root node. So here we can easily see that 3 is the parent of 1, right? So it completely depends on the root node, that which is the parent of which other node, right? And what are ancestors, guys? So all the nodes, like if I start from any node, I want to say what are ancestors of 4. So 3 is an ancestor of 4. Then 1 is an ancestor of 4. Right? That means its parent, its parent, its parent, its parent, until I reach the root node. All of the nodes which lie on the path from the root node to the current node are the ancestors. Right? So all the nodes that lie from root to current node, that lie, let's say, on the path from root node to the current node are the ancestors of the current node. I hope this is being very clear. Like the node parents, then its parent, then its parent, then its parent, and so on. Cool. So this was like another example of ancestors, child, parent, and root. I hope it is being very clear what are these 4 terms, right? So what is a binary tree, guys? Binary tree is a tree which contains at most 2 child, right? So every node will have at most 2 childs, right? So let me make some figures. Let's say 1, 2, 3, 4, 5, 6, 7. So guys, this is a binary tree, right? That every node has at most 2 children. No node has 3 children, right? It can have 0. So if a node has 0 child, that means it's a leaf node, right? So if we have a tree, we will have leaves. So what is a leaf node? Leaf node is a node which has no child, right? So not leaf, it is a leaf. Cool. And so this is also a leaf, this is also a leaf. Now 4 is a single parent, right? It has only one child. Now 3 has two child, that is 4 and 5. 2 has only one child, 1 has two childs. Cool guys, so it is a binary tree. Now see, there are different types of binary trees also. Complete binary tree is different, full binary tree is different. So that's a separate topic, right? Binary tree in itself is a very big topic. Cool. Now we have some trees on the basis of number of child they have. We have some trees like which can limit the number of childs, right? That is like we have already seen binary trees, two childs. Then we have trees which have at most three childs, four childs, and so on, right? And then we have n-ary trees. So what's an n-ary tree, guys? That any node can have n number of childs, right? So there is no strict limitation, right? So there is no strict um, there is a word for that. I'm forgetting that word. Leave. So there is no limit on child, right? So it can have n number of childs here. So yeah. So this is about entities, right? So let's make some examples. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Always remember, guys, it should be connected and it should not contain cycle. That's a tree. Cool. So here we have understood what are types of trees on the basis of weights, on the basis of childs they have, right? And on the basis of their edges, whether they're directed or not. Cool. Now we will see how to represent trees because
So some students are saying like we can move to further, uh, we can move to higher concepts like
Yes, okay.
code. We can start solving questions.
Okay. I thought
Yes.
we had beginner similar. I can teach any topic. There are very topics.
Some are saying I am beginner and some are saying I'm not. So there is the yours
Cool.
over there.
So we can say that the beginner part is done. Now let's move on to some advanced part. Cool.
Is it cool for everyone?
uh, we can have some very advanced algorithms, we can have some intermediate algorithms, whichever.
Uh,
Okay, so there are coding part, not advanced. Okay.
okay.
Okay, so half an hour I'll take some beginner level uh, problems, and then another half an hour we'll have some advanced algorithms. Cool. Okay, so people need algorithms. Cool. So let's move on to the coding part, right? So let's move on to the code part. So it's very easy, guys. How can we perform? How can we store trees? So let's say I have this tree, 1, 2, and 3. And it's very simple. We all know what is an adjacency list representation of trees and graphs, because now I'm moving on to some advanced part and I won't be like going into the detail of every topic. Cool. So yeah, so here we have 1, 2, and 3. So this is a list, and now what we'll do is we'll have an adjacency list of all these nodes. So what is an adjacency list? All the elements which are adjacent to a current node, right, will come in its adjacency list. So from 1, 2 is adjacent and 3 is adjacent. So we have two nodes which are in adjacency list of 1. We have one node which is adjacent to 2, that is 1 only, right, because 1 is directly connected to 2. And from 3 we have one which is adjacent to 3, right? So let us code it a little. Let's like make a normal tree. So if I have four, so guys, very simple. This is new.cpp on the left hand side. You can see this is input.txt. On the right above you can see, and here we have output.txt, right? So what will my code do? It will open the file input.txt, read input from it in standard input, that is cin. And what will what will the second line do? This will open the file output.txt, which you can see on the right down side. It will write to this output. Cool. So whatever I'll see out, it will come to output.txt. Let's say see out 10. So it came to output.txt. Cool. So let's see out workshop, and it comes to output.txt. Now let's take some input, right? So as I said, if I have four nodes, then it is automatically understood that I'll have three edges, because n minus one edges, right? So let's say 1 and 2 are connected, 1 and 3 are connected, and 3 and 4 are connected. So this is another tree, right? So let's take the input, and let's make a tree. So guys, generally in competitive programming, what we do is we take an adjacency list, very big, right? And what we do is we push back all the elements in the adjacency list. So let's take a vector int graph n, that is this n is very big, right? So what we have is we have an array of vectors, right? So this is an array, graph array, in which what I will do is this is basically an adjacency list, right? So let me iterate from 0 to n minus 1, because n minus 1 edges will be there. So let's take input as x and y, that there is an edge from x to y. Cool. Now we have taken the input as x and y. We will simply push back, in x we'll simply push back y, and in y we will simply push back x, right? So this is the basic representation of trees when I code, right? So as we can easily see that this is a vector array. So we have a whole adjacency list of vectors. Now what I'm doing is, in vector of some node, I'm trying to push all the nodes which are adjacent to the current node, right? So this is a normal input of trees, right? So let me print this. So see out I, and let's go in the adjacency list of I, and simply let's print it. Cool. Okay. So we can see now that 1 is connected to 2 and 3. So let me make this tree in the as in the input. So we have 1 is connected to 2, second edge is between 1 and 3, third edge is between 3 and 4. Right. So 1 is connected to 2 and 3. We can easily see 1 is connected to 2 and 3. 2 is connected to 1, right? 3's adjacency list is 1 and 4, correct? And 4th adjacency list is 3, right? So let me actually check this. Uh, we have suggestions, give us algorithms. Right, so I started with the coding part. Cool, no doubts here. So this is the basic input of an adjacency list of a graph. So this might be one of the shortest input you'll ever see, because I haven't done much here. Generally what people do is they take classes, they take structures, they write the methods of the classes to take input, right? So that's also fine, right? That's also fine. But if I want to like have a speed code and do like a little bit of competitive programming, and I want to solve more problems in a speedier way, then this is a better approach, right? Because from this we'll save our time to code, and we'll invest more of our time in problem solving and not coding, right? We'll think it will be more about logics. So guys, there's a traversal called DFS. So let's perform a DFS, right? And what we will do is, as I explained above here, we will simply we'll store like parents of all the nodes, parents of all the nodes, right? So what we'll do is we'll simply start from a root node, and we'll store parents of all the nodes, right? So let's take an array called parent, right? So we have taken an array of length n, and let's start a DFS. So for now, I'm taking the root node to be 0. I'm passing 0 to be the parent of 1 for now, right? So DFS int current node in which I am on, and this is a parent node, right? So what? So how do we perform DFS, guys? We all know how do we perform DFS. We iterate over the graph, and let's say we go over the current adjacency list, and we say if x is not equal to parent, then simply DFS x, and we pass current as a new parent, right? So here what we do is parent of current is equal to the parent that is being passed. So there is this parameter that I'm always passing in my depth first search, that which is the parent, right? So if I started from the root node, I move one step down to its adjacency list. So this is the adjacency list. This is I'm iterating over all the adjacency list. So here x is an element which is in adjacency list of current, right? So out of all the elements, we will have one parent, because a parent is a node from which I'm coming right now. So that has been passed here, right? And now what is the condition that I'm checking here? X is not equal to parent. So if x is not equal to parent, I'm simply traversing down, right? So that's a DFS algorithm. It works on recursion, right? So this is a recursive approach of traversing in a tree, right? And let me like print things here. So here we can easily see I've stored the parents, right? And as already explained, that the parents are always dependent on the root node, right? So whatever is the root node, parents are always dependent on it. Cool. So yeah, so let's print them one by one, and then we will like cool. So right now I'm just thinking that we know this much. What is a DFS? And let me quickly code a BFS. So what is a BFS, guys? What is a breadth first search? So breadth first search is normal to is like an iterative approach, right? So if DFS is a recursive approach, then BFS is an iterative approach. So how do we perform a breadth first search? We start from a node and we like go around it, right? That means okay, let me take an example. So guys, how the DFS on this graph would work? So firstly I'm on 1, then I may go to 2, right? Then 2 will go to 6, then I'll come back, right? I'll come back to 2, come back to 1, then again I'll go to 3, I'll go to 4, then I'll come back to 3, I'll go to 5, come back to 3, come back to 1, and go back, right? And how does a BFS work, guys? So what does BFS do? Firstly, BFS, there are different types of breadth first search. So there's this single source BFS, then we have multi-source BFS. So for now, let's like deep dive into single source BFS, right? So what is a single source BFS? Single source BFS is that, let's say if I'm starting and I'm trying to apply BFS from 3. So I will be on 3, then I will visit 1, 4, and 5, because these three nodes, see, this has a distance of 0 from 3, right? These three have a distance of 1 from 3. And then I'll visit 2, which has a distance of 2 from 3, and then I'll visit 6, which has a distance of 3 from 3, right? So basically, guys, what does BFS do? It visits all the nodes like a BFS, right? So basically think that there is a still water and we are like dropping one drop of water in that. So we can easily see that it goes in all directions in like equal parts, right? It is evenly distributed in all directions. So it's same, the BFS is the same thing, right? First 0 node, then it will visit all the elements of the first node, then the second node, then the third node, and so on, right? So let me like, as I have coded out DFS, let's code out BFS too, right? So void BFS, and in this BFS I'll pass a source node. So let's not write current here, let's write source. Cool. So in this BFS I'll be passing a source node, and initially let's pass the source nodes to be 1. Now what, how does the BFS work? It takes a queue as a data structure, right? So queue dot push source. So let's push source inside the queue. And after this, what we need to do is, yeah, so of course, guys, we would be needing like an array like, which will tell me that whether a node is visited or not. So let's take a visited array, right? Of course, guys, whenever we are like traversing in trees, right? So there's the difference. If I perform a depth first search on a graph, I will be requiring visited array, right? I'll be requiring visited array to keep track of the nodes which are visited. But when I perform a DFS in tree, then I don't need a visited array. Why? Because I can always keep track of what is the parent. That means I have to go to all the other nodes which are not parents. And similarly, for all the other nodes, doing the same thing recursively, keeping track of the parent so that I don't go back to the parent and recursively going downwards. Cool. So how do I perform a BFS? We can keep track of parent too, but let's keep an visited array here, and let's say that let's mark visited to be 0. Cool. Let me take above with parent only. Right. So I have a visited array. So what do? Is we mark source to be visited, right? Because it has been visited. Now what we say is while not q dot empty. While the queue is not empty, just take the front element of the queue, that is the current node which I am on. So let's say queue dot front, right? So this is the front element of the queue. Then let's remove that element from the queue. And finally, what do? Is pick up the first element, remove that element, and then we will push all the adjacency list of the current element into the queue, right? And I will only push it if it is not visited. So if not visited x, queue dot push x, right? And of course, when I'm pushing it into the queue, I'll mark it as visited. So I'm marking it as visited and pushing it into the queue, right? So this is like another. So this is an example of breadth first search. So let me like print current so that we can, yeah. So as we can see here, what we have is we have 1 2 3 4. So in this graph, guys, firstly what happened, I was on 1, then I have two options, either to go to 2 first or 3 first. So I'm going on 2 first, then I went to 3, and then I went to 4, right? Let's start the BFS from some other node, right? So let's start BFS from 3. Let's build it. So as we can see, from 3 I'm going, so it is 3 here, right? So firstly I'm on 3, then these two nodes should be visited because they are at a distance of 1 from the current node, and then the distance 2 will be visited, right? Because 2 is the farthest node from 3. Cool, guys. So we have got 3 1 4 and 2. Now guys, let's do distance part. Cool. Let's try and find out what are the distances of nodes from the source node in my BFS only, right? So what I'll do here is, guys, I'll simply say that let's take a distance array. Distance. So I've taken an array distance, and I simply say that okay, distance of source from the, okay, source. Distance of source is 0, right? Because I'm right now finding out the distances from the source. Distance, right? So what is the distance of source? It is 0, right? Now let's say I'm on some vertex and I'm going to its child. So what is the distance from that vertex to its child? It is 1. So what will be the distance of that child from the source node, right? So right now it is like this. Let's say I have a source node. So from source node, a distance to x is known, which is distance of x, right? From x I'm going to its child, let's say y, and I know the distance is 1 here. So what is the total distance, guys, of y? So distance of y will be equal to distance of x plus 1. uh okay, just a second. So here is this comment that I was reading. Uh, so Argun, we have like questions here that they are saying that beginners won't be able to do many things tomorrow.
What I understand from this comment is like the someone is saying like the way everyone is teaching so many topics per day, I don't think beginners will be able to do so many questions tomorrow. But as we all know, these are YouTube videos. So YouTube videos, you can watch a certain part of it, then you can start solving the questions and again consult to the same video and do the further process. So it's better that we complete the topic in 2 hours. Like you are getting the content of 2 hours, but it's up only up to you. Like you want to pause this video out, go to the lead code, go to the code chef, go to code forces, solve the questions out, and then come back and start the other part. If it's basically your own criteria, I think. Uh, but anyway, you guys feel we can move forward like that.
Oh, actually, I thought, matlab, I read it in such a way that it was feeling to be like कि the way I am teaching so many topics, so beginners won't
No,
be
no,
able
no,
to.
no, no, sir, you are
So
teaching really
I
good.
missed,
It's
I
not like
missed
that.
everyone. Right.
Yeah. Even I'm learning along with you because I'm also a sophomore right now and I'm also learning these all concepts with along with you guys.
Cool. So let's continue. So I hope
Yeah.
the pace is good, right? If you want me to go a
Yeah.
little fast, I can even go that, and I can also go slow. So it's on you,
So you guys can drop your comments out. We will go with that phase.
right? So coming back to like BFS, now we know that the distance from source is from distance of source from source is 0, right? So what we'll do is whenever we are moving on to any node, whenever we are like pushing it back to a queue, whenever we are marking it as visited, we will simply say the distance of x is equal to distance of the current node, that is the parent of x, plus 1, right? So we are on some current node here, right? And we know what is the distance of current node because when the current node was pushed into the queue, then its distance was marked, right? So what we are doing is we are finding out the distances of all the nodes in the BFS, right? So after the BFS completes, let us print the distances, right? So let's start from 1. Let's go to all the nodes and let's say cout I, and let's say distance of I, right? Okay, so what we have is from so we started the breadth first search from 3, right? So right now what we are trying to do, we are trying to find out the distances of all the nodes from the node number 3, right? So yeah. So initially what we did, we marked the distances of 3 as is to be 0, right? Now we are moving on to the nodes which are adjacent to 3. So their distances will be 1 and the distance of 2 will be 2, right? So as it's the same we can see over here in the output that we get distance of 1 is 1, 2 is 2, 3 is 0 and 4 is 1, right? So from any node, I can find out distances of every other node using BFS or DFS, any traversals, right? But to find the shortest distance, BFS is like trustworthy, right? So when we talk about shortest distance in unweighted graphs, then we generally use BFS because BFS algorithm, this whole BFS, it works on the basis of shortest distances, right? As I've already told you, firstly 0 distance nodes will be visited, then 1 distance node will be visited, then 2 distance nodes will be visited, and so on, right? So this is like a normal BFS and normal DFS. So these are the two important traversals of my tree algorithm, right? So yeah, every problem in tree, guys, every problem in tree will be solved using either DFS or BFS. There's no other way, right? Only DFS or BFS, there's no other way. So it will be like if you really want to like go deep into like trees and algorithm trees and graphs and its algorithms, you first have to understand what is a DFS, how does a DFS work, what is the BFS, how does it work, where can be used, then we can move on to some really nice problems, right? So these are like the basic traversals, DFS, BFS, and so guys, in the next section, I think I should go now a little intermediate, right? So is cool, guys. So tell me if any one of you wants if you have any topic which you want me to explain. Is there any topic in your mind, that any topic, like any topic, so that okay? So it's about कि BFS समझ नहीं आया, राइट? कूल, मैं सोचा थोड़ा तेज चलता हूँ, तो कूल है, थोड़े स्लो चलते हैं. सो गाइज फिर से देखते हैं BFS, है ना? एक बड़ा सा ट्री बनाते हैं अब. तो वही है, कुछ कर रहे हैं तो अच्छे से ही करते हैं, है ना? Cool. So this is a very big tree, and now let's say I want to start a BFS from 4, right? हमें 4 से BFS start करना है. 4 is the source node. Cool. So what I did was, ध्यान से देखना, if I start BFS from 4, I'll pass 4 as the source node. सबसे पहले मैंने क्या किया? I took a queue, right? So let me take a queue. So let's say this is a queue structure, and initially what I did was I pushed I pushed source in my queue, right? So I need to start BFS from 4, so I'll push 4 in my queue, right? So right now 4 has only right now the queue has only one node, which is 4, right? And the second step was I marked 4 as visited, right? So let's mark it as visited. So I'm just writing 1 over here, right? That means this node is visited. Now guys, in the next step, what happens? Right, so right now let's ignore the distance part, because once the BFS is clear, this will automatically become clear, right? So let's ignore the distance part. Cool. So let's say while not q dot empty, that means until and unless q is not completely empty, what I'm doing is I am picking up the front node, right? So right now the front node is 4. So I am picking up the node 4, that is this current is equal to 4 right now, and I'm popping it from the queue, right? So what does q dot pop do? It will simply remove 4 from my queue, right? Right now the queue is empty, but I have a for loop to iterate to, right? So what does this for loop do? It will go on all the adjacency list of the current node, right? जो भी current node है उसकी पूरी adjacency list में जाएगा, right? So what is the adjacency list of 4, guys? So 4 की adjacency list was 3, 9 and 7, right? 3 is adjacent to 4, 9 is adjacent to 4, and 7 is adjacent to 4, right? So what it will do is it will go on in the adjacency list of the current node, and it will check कि अगर वो visited नहीं था, that means if it is not visited, mark it visited and push it back into the queue. Cool. So tell me, is 3 visited? No, right? Because 3 पे हम कभी गए नहीं. So what it will do is it will mark 3 as visited and it will push it back in the queue. So 3 will be pushed in the queue. Now it will mark 9 as visited and it will push it back in the queue. Now it will mark 7 as visited and it will push back into the queue, right? Now we can easily see that after this for loop ended, जब ये for loop खत्म हुआ for current equal to 4, we have these 3 elements in my queue, that is 3, 9 and 7, and they are marked as visited. Now guys, in the second lap, now what happens is now the current becomes 3. So if current is equal to 3, that means I have to pop it from the queue also, right? So it means that I'm coming in the second iteration of the while loop, right? That queue is not empty because we had these 3 elements, and current is equal to q dot front, which is 3. Let's remove 3 from the queue, right? So always remember the front means which is in the front of the queue, and pop will always remove from the front, not from the back. It's a queue, right? It is first in first out, right? So 3 came inside the queue first, so 3 will go outside from the queue first. So current is equal to 3, guys. Now we are on this 3. Now tell me, what are the adjacent nodes of 3? So 3's adjacency is 1, 4, and 5. So these 3 nodes are adjacent to 3, right? Out of these 3 nodes, if I iterate on them one by one, let's iterate on them one by one. Let's go to 1. So tell me, is 1 visited? No, we can easily see we never went to 1. So we'll mark it as visited and we'll push it back to the BFS, right? Then we will move to 4. So guys, 4 is already visited. So I don't have to go to 4 again because 4 is already visited, right? So I won't perform my breadth first search on 4 again. Otherwise, we'll stuck in an infinite loop, right? 4 to 3, then 3 will push 4, then 4 will push 3. So that's why we need a visited array. That if an element is already visited, then don't visit it again, right? So that the complexity of the algorithm remains O of n. So when the adjacency list will move to 4, it will simply say that it is visited. So if the node is visited, I won't go inside this if. That means I won't be pushing it into the queue. Now let's move on to 5, right? So when I came on to 5, I have moved on to 5. As we can easily see that 5 is not visited. So what it will do is it will mark it as visited and push back 5. So are you guys getting this, that we started from 4, now we are traversing 3, 9, and 7, then we are traversing 1, 5, right, and so on, right? So in the next iteration again, guys, what will happen? It will pick current is equal to 9. See, current will be equal to 9. All the adjacent nodes of 9 will be pushed back into the queue. So this is 9. There's only one node which is adjacent to 9, which is 4, and it is already visited, so nothing will be pushed inside the queue, right? So in the next iteration again, 7 will be picked from the queue. So where is 7? Yeah, we have 7 over here. So adjacency list of 7 contains 4 and 8. 4 is already visited, so 8 will be pushed in back of my queue, right? Now we'll move on to the next iteration. 1 will be pushed, 1 will be picked up in the next iteration, and adjacency list of 1 include 2 and 3. 3 is already visited, so 2 will be pushed behind my queue, right? So after 9, where did we go? We went to 7 and we went to 1, right? Yeah. So in 1, 2 will be pushed, right? And it will be marked as visited, right? And now what we'll do is we'll pick up 5, and this 3 and 6 will be 6 will be marked as visited, will be pushed back by my queue. Then current will be equal to 5, then current will be equal to 8, then current will be equal to 2, right? So when the current is equal to 2, guys, 10 was an adjacent element of 2 which was not visited, so 10 will be pushed behind my queue, right? So after 5, after 8, after 2, 10 will be pushed, so these will be removed from my queue. Let's remove them one by one. Now 6 will be picked, all its adjacent elements are already visited, and finally 10 will be picked up, right? So 2, 6, and 10. So guys, this is the order in which in which BFS will be performed, that is 4, 3, 9, 7, 1, 5, 8, 2, 6, and 10. So we can easily see this is the distance 0 from 4. These 3, 9, and 7 are at a distance of 1 from 4. 1, 5, 8 are at a distance of 2 from 4. 2, 6 are at a distance of 3 from 4, and 10 is a distance of 4 from 4. So we can see this order of BFS, right? That the first nodes are the closest ones, then the other nodes. Cool. I hope this part is really being clear of what is the DFS and what is the BFS. Okay. Clear. Cool, Akash. So great. So now let's move on to a problem. Let's say I have a problem, and what does that problem say? Problem says that, okay, uh, you have been given a tree and two extra nodes, two nodes. Let's call them x and y. So what we have? We have a tree and we have two nodes x and y, right? What we need to do is we need to print our path from x to y. So print path from x to y. So we know, guys, if it's a tree, that then path from x to y will be unique. That's a definition of the tree, that it will contain only one path, right, between every pair of nodes. So we want to print a path from x to y. For an example, take this example. Here I want to print path from uh, 4 to 6, right? Let's say x and y are 4 and 6. So what's the path? Path is 4, 3, 5, and 6, right? And I want to do it in a linear time, right? I don't want to apply backtracking here. I want to do this in a linear time. So how will I do it, guys? Use this concept that I've already told you. Use the concept of root. It's a hint, right? You want to print a path from 4 to 6. So how will you do that? So one very simple thing will be that from 4, calculate all the distances from of the other nodes, right? Cool. That will become a little advanced. Let's get on with very simple approach of this algorithm, right? So guys, what we can do is, yeah. So what we can do is, I'll tell you a very simple approach, that make 4 as a root node. Make 4 as the root node and perform a DFS. Right. So how will the DFS work? From 4, I'll have 3 child, that is 3, 7, 9. Cool. From 3, I will go to 1, 5, 6, 2, 10, and then from 7 I'll go to 8, and 9 will be as it is. So guys, we can easily see that if I make 4 as the root node, what is making it a root node? Just pick it up and hang the tree from the 4th node, right? So if I hang the tree from the node number 4, then simply we can see that this will be the structure that is formed in the DFS, right? So what I have done is, if I have two nodes x and y, from whose path I have to print a path from x to y, right? So I will pick the node and pick the node x, make it the parent, make it the root node of the tree, right? Now guys, what I will do is I'll perform a normal DFS and store all the parents, as I already did. Where is the code? Yeah, here is the code. So here what I did was I stored all the parents of the node, right? For every node I stored the parents by considering it 4 as the root node. So let's consider 4 as the root node and store all the parents. So 3's parent is 4, 4, 4, 7, 3, 3, 1, 5, and 2. So these are the parent nodes, right? So what I have done is I made x as the root node, and I want to go from y to x. So we all know that if x is the root node and y is somewhere in my tree, what I can do is I can simply climb parent by parent, and finally I'll reach the x node, because it is the root node. It is the ultimate parent, right? So I wanted to print a path from 4 to 6, right? So where is 6 here? This is 6, right? So from 6, I'm starting from 6, I'll go to its parent. What is parent of 6? It is 5. What is parent of 5? It is 3. Parent of 3 is 4, and I'll stop here because I have reached the root node, right? So if you want to print a path from node x to node y, simply make x or y the root node, store all the parents, and then jump parent by parent, parent by parent, and go up, and you will get the path. Cool, guys. So let's code it out. So okay, so DFS is already written, and let me comment the BFS also. Let's print path from cool, let's take a big example. let's take this example only. So here we have 10 nodes. The edges are between 1 to 1 3, 2 10, 3 4, 3 5, 4 9, 4 7, 5 6, 7 and 8. Right, so 10 nodes and 9 edges. Cool, right? So this is a normal DFS that I am performing, right? And of course, as I said, I want two other nodes which are X and Y, right? So let's say X and Y, let's keep it over here only. So X is let's say 3 and Y is, let's say, 10. So I want to find a path from 3 to 10. So what I'll do is I'll apply a DFS from 3. So according to 3 as the root, all the parents will be stored into this parent array, right? So all the parents will be stored into the parent array. Now after this, guys, what will happen if I have all the parents? I'll simply start from Y. So let's start from Y, right? So while Y is not equal to X, cout Y, uh, just a second. Yeah, sorry. So where were we? Yeah. So we'll start from Y. We'll keep on going to X, right? Until Y is not equal to X. And what we'll simply say, we will say that print Y, the node, and simply make Y is equal to parent of Y, right? So parent is capital P. So very simple, guys. We are starting from Y, printed Y because it was in the path, and now what we are doing is we are simply moving one step ahead. So we are saying Y is equal to parent of Y. Now this is the new Y, right? One step above one, the parent. Now this is the new Y. We'll print it and then we'll again move to the parent of it. So we'll keep on going above until Y is not equal to X, and finally we will print out Y, right? Because finally we are moving on to X, right? So let's build this. We can see that what is the path from 10 to 3, 10 to 1 and 3. So here is your answer, right? So I hope you got this. What does why do we need to make any one of those nodes as a root node? So guys, this is one of the simplest approaches of printing the path, right? Of course you can store you can keep a vector in the DFS, right? But that would take a huge complexity. It would be an n square complexity, right? So what we have done here is we have simply performed one DFS, and we are like moving on to parent by parent, parent by parent until we reach the root node. So let's take some other example. Let's say 6 and 5. So what's the path from 5 to 6? Okay, they're directly connected. So let's say 6 and 10. Right. So this, just let me cancel the build. Okay, so there is something infinite which is going here. Right, no problem with that. So guys, I hope you have understood this part. And is there anything you want to understand? Okay, you want the code. Common ancestor. Okay. Yeah, Akash. This could also be a valid solution, that you can move on to some common ancestor of both the nodes, right? But the best is simply make one as the root node, right? And simply go to the root node. Otherwise, you have to take two pointers. Keep from this also and from this also. I'm going above one by one, right? Okay, I'll share the code. I'll give it to them, and so I think I'll be finishing the workshop over here. If you have any doubts, you can let me know. Okay, and also let me tell you that we have like earlier I used to teach at coding blocks. Like I've been like spent my 2 years at coding blocks, and my students are in like Google, Facebook, everywhere, of course, right? And I've also taught industry level people also, right? Those who are already like working and they want to learn data structures and algorithms like side by side. So now what we have done is we have like started our own platform called Coding Minutes, in which we'll be like we are making courses. So it's just begun, right? So here we have Pratik Bhaiya, who is like the founder of this. And what we are doing is we are like bringing some courses in really really very short, like very low price, like around 300 or 400. So if you want to master any particular uh, particular topic like graph, DP, anything, right? Anything in computational programming and data structures. So we have this website like Coding Minutes where you can go and enroll, right, for all the courses. Yeah. So it's just beginning, of course, but yeah, we would be like making it grow. So in this, I am like applying my previous 2 years knowledge, that whatever I've got from whatever questions I have done, I'll be applying all the knowledge in these courses. I'll like save all the knowledge here. It is available on Udemy, so you can simply check it out. Cool. So that's from my side. Anything else, Argun?
Uh, any of you have any queries? You can share now. Okay. I feel, sir, like you have solved our many queries. Thank you for joining with us for such an amazing session. We really appreciate your patience with us, and thank you for being available with us for more than 1 hour. And anyone having any queries?
Uh, if
I
there
think
are
many of yes, sir.
if there are no queries, then it only means one thing, that I've taught very well, because doubts ही नहीं आ रहे हैं, right?
हाँ ये भी हो सकता है 30 से ज्यादा बढ़िया समझाएगी सर someone is saying like हर जगह स्ट्रक्चर मिल रहा है that how to solve in vectors आपके पास है कोई मतलब वीडियो
हाँ, तो ये जो मैंने इसमें वेक्टर ही तो लिया था, एक सिंपल वेक्टर एरे लिया, नथिंग एल्स। मतलब बहुत जगह देखोगे वहाँ पे क्लास होगी, स्ट्रक्चर्स होगी, पॉइंटर्स मैनिपुलेशन होगा, राइट? बट दैट इज गुड, मतलब जनरली जैसे इंडस्ट्री लेवल वगैरह में वही यूज होता है ना? हर जगह वही यूज, जैसे मैं जोमेटो में काम किया तो वही यूज हो रहा है। बट हेयर व्हाट वी आर ट्राइंग टू फोकस इज, हमें डेटा स्ट्रक्चर्स एंड एल्गोरिथम्स जल्दी से जल्दी करना है, राइट? तो हम नहीं चाहते कि हम अपना मैक्सिमम टाइम कोड में वेस्ट करें। वी वांट कि हम जल्दी से सोच लें, वो एल्गोरिथम इम्प्लीमेंट कर लें एंड मूव ऑन टू द नेक्स्ट प्रॉब्लम, राइट? बिकॉज आवर टारगेट इज सॉल्विंग एज मच एज प्रॉब्लम्स इन एज मच लो टाइम एज पॉसिबल, राइट? सो इसलिए, और कंप्यूटर प्रोग्रामिंग में भी यही होता है, दैट वी हैव टू सॉल्व प्रॉब्लम्स इन रियली वेरी फास्ट पेस। जल्दी जल्दी करने हैं, राइट? लाइक 2-2 मिनट में प्रॉब्लम्स कर देते हैं लोग, तो पढ़ पढ़ भी लेते हैं, कोड भी कर लेते हैं। सो इट्स बिकॉज ऑफ दीज ट्रिक्स एंड टेक्निक्स ओनली कि दे आर एबल टू लाइक कोड रियली फास्ट। वरना स्ट्रक्चर क्लास वगैरह बनाने बैठेंगे तो 10 मिनट तो उसी में लग जाएगा। देन
या
पब्लिक प्रॉपर्टीज एंड ऑल दैट, राइट? तो दैट्स गुड फॉर इम्प्लीमेंटेशन पर्पसेस, राइट? उसका अपना फायदा है, right? But here what concerns to us is solving more problems in less time. So that's it.
sir can you share the link of coding minutes I think someone is asking like working persons के लिए coding minutes पे कोई कोर्स है क्या
देखो, कोडिंग मिनट्स अभी शुरू हुआ है, लाइक अभी 2 ही कोर्स हमने डाले हैं, राइट? एंड बिफोर दिस कोडिंग ब्लॉक्स में पढ़ाता था मैं, राइट? सो कोडिंग मिनट्स में वी आर लाइक ग्रोइंग इट, जल्दी जल्दी कर रहे हैं, ऑफ कोर्स। एंड ऑल्सो द प्राइसेस आर वेरी लो, लाइक 300-400 में तुम्हें एक अच्छा कोर्स मिल जाएगा, जिसमें तुम्हें सारे टॉपिक्स कवर होंगे फॉर अ पर्टिकुलर टॉपिक, डीपी ग्राफ, है ना? एंड देर इज दिस लाइक डेटा स्ट्रक्चर्स एंड एल्गोरिथम्स कोर्स which is only in 490 rupees, and it's not much, right? So it's not for like monetary values ki we are doing this. We are just placing all our knowledge into these courses so that people can learn and grow, right? सो ये codingminutes.com है डायरेक्टली. यहाँ पे इस डेटा सेक्शन से एल्गोरिदम कोर्स को यू कैन गो एंड ट्राई, एंड then you can also of course try our other courses too. codingminutes.com. बस that's the least expected from a software engineer. मतलब कोई सॉफ्टवेयर इंजीनियर बनना चाह रहा है तो वो इतना तो याद कर ही सकता है. Any other thing? अच्छा, why not use stack instead of queue? For what, Rohit? For for BFS? See, for DFS जो रिकर्जन बन रहा है वो स्टैक में ही बनता है, राइट? तो एक तो DFS को हम रिकर्सिव भी लिख सकते हैं, और एक हम DFS को स्टैक के थ्रू भी कोड कर सकते हैं by taking a stack. Right, what we'll do is always push elements at the back of the stack and remove the last element, then again push the elements at the back of the stack, remove the last element. जैसे हम क्यू में कर रहे थे ना, आगे आगे पुश कर रहे हैं, सॉरी पीछे पुश कर रहे हैं, आगे से निकाल रहे हैं. बट स्टैक में हम क्या करेंगे, विल सिंपली पुश बैक एंड रिमूव फ्रॉम बैक ओनली, सो दैट विल बिकम DFS इंस्टेड ऑफ BFS. राइट, सो दैट्स द डिफरेंस बिटवीन BFS एंड DFS. DFS डेप्थ में जाता है पहले, राइट, बिकॉज इट इज पिकिंग द लास्ट एलिमेंट, but BFS will go in the breadth first, right, because it is picking up the first element from the queue. Yeah, Shivansh, I can't like answer this correctly कि what type of questions of trees are mainly asked in the interview. मतलब मैंने 3 इंटरव्यू दिए, मेरे तीनों हो गए, और मेरे इफ आई गिव यू अ परसेंटेज, सो 70% ऑफ द क्वेश्चंस वर फ्रॉम ट्रीज. सोचो, ट्रीज एंड ग्राफ्स के एल्गोरिदम से 70% ऑफ द क्वेश्चंस, वो भी कोऑर्डिनेशन, जोमेटो, गूगल, इन कंपनीज में. सो ऑफ कोर्स ट्रीज एंड ग्राफ की काफ़ी वर्थ है, राइट. एंड इन द नेक्स्ट 2 वीक्स मतलब मैं एक ग्राफ का कोर्स बना भी रहा हूँ जिसमें बिगनर टू एडवांस सारे ही एल्गोरिदम कवर होंगे अच्छे से विद कोड. सो यू कैन ऑल्सो चेक दैट आउट ऑन कोडिंग मिनट्स. मतलब 1-2 हफ्ते में आ जाएगा आई गेस. हाँ आकाश, मैं बताया ना, मैं एक कोर्स बना रहा हूँ, बहुत डीप में समझा रखा है और सारे टॉपिक्स हैं. मतलब उसमें क्या होगा कि यू वोंट फील मिस्ड आउट ऑफ एनी टॉपिक. जैसे कहीं भी तुम कोई भी प्रॉब्लम सॉल्व कर रहे हो, उसमें कोई टॉपिक लग रहा है, वो टॉपिक विल ऑलरेडी हैव बीन कवर्ड इन दैट कोर्स, राइट. एक्सप्लेन वाई नॉट इक्वल टू एक्स, ग्रेट. तो मैं एक बार समझा देता हूँ फिर से. तो गाइस क्या हुआ कि हम y पे थे, राइट, और हमें रूट नोड तक जाना है. व्हाट इज द रूट नोड? x. तो हम क्या कर रहे हैं, वी आर स्टार्टिंग फ्रॉम लेट्स टॉक अबाउट 6 ओनली ना. तो y is 6 एंड x is 4. तो y लूप कब तक जाएगी, हमें कब तक ऊपर जाना है, हमें कब तक पेरेंट पर जाते रहना है, जब तक y इज नॉट इक्वल टू x, राइट. दिस इज x. तो हमें यहाँ से लेके पूरा यहाँ तक जाना है. सो वी आर जस्ट मूविंग ऑन above until we can, right? Okay, any other doubt guys? Cool. If there are no more doubts, then grant me leave, right?
Uh, Thank you guys, and thank you sir for joining us. Uh, stay tuned to the bootcamp, and we are having our contest tomorrow over Coding Ninjas platform. So all of you register for that, and if you have any queries regarding the contest, you can leave here. Thank you.